Ishan Rao, and I'm a PhD student, and this is the sixth live interaction session for the deep learning course. And in this sessions, now previously we have looked mostly the course from the code perspective and some math and some theory aspect. Here in this course or in this session also, we are going to do a mix up of that. And we will be looking at the optimization. Last time we thought of using the PyTorch for deep learning directly, but before that you should know few more concepts before directly using the PyTorch or TensorFlow libraries to build all the stuff. Okay, so we will going to discuss mostly the optimization aspects with respect to the gradient descent, that is how to update the parameters and all, what are those different algorithms. Obviously you might have heard the same topics in the week 4 or week 5 of the course. We're going to touch that aspect, that is different type of gradient descents. With respect to their code, we will I'm not going to code any stuff, but we are going to run the code simulation, so I'm going to provide that thing as well. So I will switch between my second devices and this current device, where in this the screen that you're sharing, we will discuss some theoretical aspect, followed by we will see the code, and we will try to experiment different variations on how to understand certain concepts of why the optimization is needed. Okay, so when we say optimization, it's basically to reach, in this case as of now, to reach to reduce our loss function as fast as possible. So this is in terms of optimization we are talking about. Okay, so let's start with the this today's thing. So if you have any question, please type down in the chat section. Okay, so so deep learning so far till with respect to the what we have seen in the introduction sessions and all, the last 5 sessions, it's basically about that we have seen sigmoid neuron, feed forward, and back propagation. Okay, so we have seen that we reached to a stage of sigmoid neuron, and from how sigmoid neuron we build the feed forward neural network, and from feed forward neural network we have adapted, we incrementally we have introduced the concept of back propagation to update the weights. Okay, till now this is what we have seen. Now if we have to see from the historical point of view, whatever we have seen here we can compromise into till 1980s kind of timeline. Okay, these things and most of the other stuff that you have seen will be there till 1980s kind of stuff. But what we have seen, the emergence of deep learning happens after 2006 or let's say 2010s, right? So we have seen the emergence of deep learning more prominently, right? That in the last decade, last 13 years, we have seen with respect to that. Now, so what has been changed? So let's say like 2006 till 2023. So what change actually happened that we are starting using more and more deep learning, right? So here we are. So what we got is something called as better learning algorithms. We got better learning algorithms, better initialization, better activations, and better regularizations. Okay, so whatever in last 5 sessions we have seen, we hard coded the back propagation and hard coded the feed forward networks and other things, right? Now in this occasion, because of computational improvement and all that, we have seen much better algorithms. Okay, obviously we also get more data and more computing power, right? So these are some emergent concepts with respect to this. Now today we are going to talk about basically 2 aspects in this case as of now, that is these 2. highlighting with blue box, that is better learning algorithm and better initialization. I will show you visual with proper visualization with its own code, which you can take it and you can try it on your home also, that how initialization affects, and obviously how learning algorithms will going to affect the better understanding of the data, right? So we will going to see that aspect for sure. Okay, so we are going to discuss today learning algorithm and initialization aspect, and mostly with respect to gradient descent. So let's start with the, now given the context now where we are going to now jump into actual where people started using this more. So in reality, you are not going, whatever you have learned as of now, these are the basic and this is something you should know. You're not going to implement them, but this is the basic on top base on top of which you are going to see whatever as of now we are going to use, and by default whatever you are going to use uh, in your code will be built on these topics. Okay, the topic that I am discussing. So let's start with respect to the gradient descent algorithm, and we will see its code also, visualization, and we will see the limitations with respect to that. So in a general update rule in the learning algorithm scheme that we have seen from the lectures of Mitesh sir is we have a WT, which is a weight, and WT plus 1. So it will update based on the WT, that is the previous weights, minus learning rate, we call this as eta, okay, and delta of WT, right? Now delta of WT is nothing but basically the partial derivative of loss function with respect to the weight t. Okay, so this is, we call it as gradient. These are gradients that we are calculating in our feed forward back propagation algorithms, and based on this we are calculating DWT and we are updating our weights. Same goes for bias as well. Okay, now there's few questions that we are going to we have to ask again and again. So let me go to that question that you have to think about. Okay, uh, so the question you have to think about is, you have seen that that yes, you have to update your weights with some delta W and all those stuff. So the first question you ask is, how are you computing the gradients? Okay, and which data you should use for computing the gradients. We will see as the second half of the this thing, that is after 7. What we are going to see right now is how to use the gradient and can you come up with a better updation rule. Okay, so this is what we are going to focus in next 15 minutes or next 1 hour. We are going to focus on how we use the gradients to get to the better performance of the learning algorithm, that is how to minimize the loss. So why we are talking all of this, all of updating rules or delta W is just to minimize the loss with respect to learning of our machine deep learning model, right? uh, so we will use the grade, we will calculate the gradient, how can we better work. So this is what something we are going to talk about. uh, there are some messages are coming, I will reply them maybe after a few minutes once a few aspects of this class is over. Okay, so I will reply to all of those questions. Okay, now let's first so you understand this is a typical gradient descent algorithm. This is, you're trying to find a delta W, partial derivative of loss, L is loss function with respect to weights. Okay, so now I will show you a demo. I will show you the visualization of that uh, with respect to this, and then we will come back to and discuss the actual limitation of that. Okay, so let me stop sharing the screen. I'll share my computer screen. Okay, let me share this code with you as well. I have seen a lot of messages are there. I will just come back and I will share that with you as well. Okay, so please, this is the collab notebook, Google Collab notebook that we are using from last few sessions. So if someone is not accustomed to that, please get accustomed to this, where you can learn your deep learning algorithms. You can try and test your deep learning algorithms. Okay, so in this we are going to discuss many different stuff. So quickly, I'm not going to go through each and every line of the code, but I will give you some just approximation of that, because we are more interested in learning about the output, what we want to learn with respect to that. Okay, in your own time you can go through line by line and see, understand what is what actually doing, but I will give you overview of with respect to code, and then we will see mostly interested in the output that we are getting from the code. Okay, so that being said, so I'll just give you some basic introduction. So this highlighting part is basically for visualization. This is something you don't need to learn. Even I don't know. I have taken this code from the Michesh sir and Pratyush Sharma sir and some of the outside online code. So I have taken that, modified a little bit according to my needs, and then I'm going to tell you this. Okay, you don't have to remember. This is not going to come to test or any such thing, but this is something. It's help us to better our understanding with respect to the how to understand the limitations or the better gradients that we are going to learn over the course of this session. So the first 4, 5, 6 function libraries that we are taking is from the this coming from the matplotlib MLP toolkit kind of thing, and NumPy is where we are storing our data. Now, in this session, we are only talking about with respect to sigmoid neuron. So in this this is a class, and we have defined some standardized functions. So this def init is basically for basic initialization of a parameters, which is in our case is w and b. We will go to that function one by one. This will give me an overview of the class, and then we have a sigmoid function which we return as 1 divided by 1 plus e raised to wx plus b minus wx plus b. That is there. That is the error function to calculate the loss function, to update or finding the delta w or delta b. For that we have written grad w and grad v function, and fit is our main function where from which we are calling other functions. Fit is basically where the actual running is happening. Okay, so we have so it has lots of other things, like this GD for gradient descent. There's something called mini batch, momentum gradient descent, NAG, Adagrad, RMSProp. This is something we are going to discuss in today's lecture. We are doing that, and then there's a append log where we are storing all the errors or whatever the errors we are getting, or with respect to weights, and this we are going to store in this function. Okay, so this is a class which we are going to use throughout this thing, and there's some standard format which we are using it from 2-3 classes that which makes us understandable that how the actual class of deep learning can be written. Now coming back to initialization, so we are initializing, basically we are just giving the if we are not giving any input to the w and b, we can directly take it from here, this function. So there is something called w and b. That's for parameters of weights and biases. It is scalar. That means we are not having a vectors of weights or vector biases. We are keeping one value for weights and one value for biases. That's how we are keeping it. Now there's something called a wh, then wbh. Please look at where I'm highlighting the code. Okay, if you're not able to see, just follow the cursors and where I'm highlighting. So wh and the bh and all these are history variables. Now why history? We will come back to this part when we go towards that, but as of now just understand that these are something called history variable. We again come back to this. Okay, and then this is sigmoid function, that this one dot is basically the floating point, and this for just the basic function of sigmoid we are using that, and error function, that is for each and every points in x and y we are calling the sigmoid function. We are calling the sigmoid, and we are which give a we are calling the sigmoid function, and whatever the value we are getting, we are minusing it with respect to the truth value, that is y. Okay, and we are having the mean square loss error function. So we are for each and every point, whatever the error we are getting, we are taking that, we returning it. Okay, similarly for updating the delta w and delta B, we have taken the partial derivative with respect to the loss function. So for that we got some equation. So that is y predicted minus y into y predicted into y minus y predicted into x, right? So the only this is something predefined. This is not something we have taken. This is already defined. The mathematics is already done. So even if you're not able to, that is totally fine. Just try to remember these equations as of now. Okay. Similarly for grad b, into x, we had just removed the into x part and we kept rest as it is into this. Okay, so this is for delta w and delta b, that is the weights that we're going to update in after each and every epoch or step. Okay, now this is a fit function, which is a learning function. It has something called as epoch, that is 100, that is number of times I have to pass through the whole data points, the whole data set. That is the one thing. And after that there's something called as eta, and eta is basically the learning parameter. And then we have something called gamma, Bini, batch size and all. We will look into it. That is coming with respect to the Adagrad or Adam optimizations. We will look into that, but as of now you don't have to know. Only if you know the epochs, if you know the epochs and eta, that is more than enough. Eta is basically the learning rate. Okay, now we are interested in, as of now, in gradient descent. GD means gradient descent. Let me write it as, okay, now gradient descent, what we are doing is we are traversing at each and every point of the input and we are updating the weights. First we are calculating the weights, the delta w and delta b using the grad function, and once the grad function for each cumulatively for whole points we have calculated, we are going to update that with respect by subtracting the w with its previous value, and we are doing with respect to the learning rate. Okay, and then we are appending the log with respect to whatever the w and b we have got. Okay, so let's now focus on this aspect only, that is gradient descent, because we have to see the limitation with respect to that. Now what we do is, first we will see some with respect to the experiment with how a gradient descent will look when we are going to plot in 3D points, and then we will see the limitation. So let's start with that. So here I have taken some random points of x as an input and y as an output. Okay, so two scalar inputs with respect to this, which is random inputs we have taken. We have defined algo as one of the parameters as GD, and we have initialized WB. Earlier if we have seen or in the course also, we usually initialize WB randomly, but here we will see that how the impact of initialization changes the learning of the gradient descent with respect to that, and how it is affecting the reducing the loss function. So we will look at that. And epochs is 100, that is 1000 times we are going to pass through the whole data point, that is we are going to pass 1000 times with these data points, and ETA is learning rate. Okay, eta, which we call as eta is learning rate. Okay, now W min, W max is basically it's a plotting point where that from -7 to 0.5, this is one axis, and B y axis will be like -5 to 5, and there's something called as frames. Let's keep it at 20 as of now, and we have the option in this code where we can plot both 3D and 2D. Right now we are just plot 3D as of now. Okay, so let's run this part, and we are going to plot, so we are calling the function of the Sn function. We are creating an object of Sn, that is Sn is a class, that is sigmoid neuron. So we are creating an object of that, and we are calling the fit function here, where we are passing the input, output, the number of epochs and the learning rate. Okay, and we are plotting our errors. E means errors. Let me write down. E means errors. Okay, W means weights, and B means biases. Okay, so we are going to do that, and E with respect to the EH, if you see, so that is with respect to the history. That means we are looking at the old past values of errors and history as well to plot out this thing. With respect to bias history. Now Now if you're going to run this, so what we see is the red line, if you can see, if you follow my cursor, it is basically for the errors, that is for that is basically the loss function. So we can see that it was around 0.4 or between 0.4 and 0.5, and how it is reducing to almost near to 0, but it got stabilized. Similarly, the blue line is for the weights, and you can see that how it started at the -2, that is the initialization point for us. From -2, how it is started increasing with each and every epoch. So the x-axis is basically the epoch here, and how it is increasing, increasing, and laterwards it got stabilized around after 500 epochs. Similarly for bias, it goes increases till -1 or -0.5, and how it is decreasing, decreasing till it gets stabilized around 700 or 800 epochs. Okay, so this is what we can see, that how weights got stabilized after weights, biases and loss got stabilized after certain point of time. But how to visualize it? Okay, so this is a code for that. I'm not going to go through this code, but as of now, just assume that this code is going to give us this output. So let me just increase the font size for this. So this is called as 3D plot. So above you can see this is a proper 3D plot, where you can see that the red part, okay, follow my cursor, the light red part is above and the light blue part is below than that. The dark red basically is the highest point, and the dark blue is the lowest point. The same the same 3D plot you can plot as a contour line. So what you can see at the below, okay, just a minute. I think I got disconnected with my second device. Okay. Okay, just a minute. Just let me check. Am I audible? Just please say yes or no. Yes. Okay. Thank you. I'm just to be sure with respect to that, because my second device got disconnected. That's why I was to make sure. Okay, sorry for disturbance. Let's go back. Now if you have seen in the course also, that you have seen that how we have like how we can present a 3D plot into a 2D plot using the contour lines. So if you can see here on my cursor, where my cursor is moving, the highest point will be shown as the contour point as dark, and the lowest point will be shown as a blue. And you can see there's some lines are there. These lines are basically contour line. So if there's a steep, that is like you can see that from how it is going like a waterfall. So from red it is going down as a slope, and it's going down. So in contour lines we can see that the more closer the lines, that means the more steep the slope will be, and the more plain the surface is, like in this light red you can see, or light orange you can see in the ground, and the 2D plot also, that the area is very big. The number of contour lines in this plane region is very less with respect to that, right? So you uh, I hope you can visualize that how a 3D plot can be present in a 2D plot using the contour lines, where the dark red shows the highest point and the dark blue shows the lowest point. And this is what we need to basically get an understanding to how the loss function is moving. Okay, so right now I'm just, for illustration in this part only, I'm going to show for 3D point. After that I will show most of the plots into 2D point, because that we can visualize much better, and we can see that how this thing is changing. Okay, okay, so let's go and let me reduce the screen size one time. Okay, uh, so okay, so this is a 3D plot that we are plotting, and but our interest is to actually look at how the how this loss W and B is been changing, and how the loss function has been calculated, right? So how we can plot in there. So for that, there is something called, we have defined as plot 3D animate, and if we are giving a option of plot 3D, we are following certain lines of code which tells about that. Take look at the history of the W, that is weights and biases and errors, and use that information to plot. Okay, and in this this if and else condition, we are just defining the which algo, for which algo we are doing this for. Okay, so okay, now this is the kind of animation that we are going to do. So you can see at epoch 0 we have 0.4 of 0.4 of error, right? So what you can see here is on the 2D plot of contour line, there's a red dot, and on the 3D plot there's a light brown. If we can't see, just look at my cursor. Okay, so what I will do is I'll just start one loop and just see that how it is changing. So our main goal is to go to the dark blue line always, because we want to reduce the loss, or we want to reduce the error. So error is at the z axis, x is w, and y is b. Okay, so if I run this thing, now you can see that how the line is going, that starting from the red portion, and how it is going quickly. It will take some time to go to the till the main point, until since the major slope comes, and he quickly shift it down and go till the lowest point with respect to that. Okay, so let me go step by step also, that will be much better. So let's say okay, so what happening, after one click is equal to 50 epochs. Right now I've kept 50 epochs. We can do afterwards, if you want to play with the code, you can do step by step also. So 50 epochs, you can see that it just move very lightly, the w hasn't changed much, neither the b has changed much. Then again we has taken step, that is the epoch is 100, error is less, but we can see that we're still in the red region after 100 epoch as well. So again we click, we can see that little after 150 epochs error started reducing, and we can see the certain slope is coming into the picture, right? Because you can see the light white line with respect to the red part. If you can see that red part, you can see that this some right line is coming. Okay, again after 200 epoch we have seen the greater jump, because what we found that we have seen the slope. Now once the slope is there, let's assume it has a ball. From the plane it was moving slowly, and the moment the slope came, it started moving fastly, right? So after 200 epochs, the error, which earlier was at 150, it was at 150 was 0.3. After 50 epochs, the error became 0.01, which is a quite significant. Why? Because the slope is basically because of the slope. Okay, so again we will go back, and we will say after 250 epochs it became much smaller, it is 0.005, that is approx less than 5% of error. So again we click on this. Now we can see that now the error after 300 epoch, the error starting getting slow. Why? Because we already come down to the dark blue region, and this dark blue region, and is quite plain in this part, so there's no slope. So we can see that again slowly, this, the more click, we can see that the movement of the red and the black line in this case is very less. Okay, so it's not even moving, it's very barely visible that what movement is happening, but the epochs are happening, and the error has become almost zero with respect to this. Okay, so like this we have seen. So this is what typical gradient descent learning will work, that at the plane region it will go slowly. When the slope will come, it will learn very fastly, it will go down. That's why gradient descent we are talking about. We want to find the minima with respect to the plot, and then once it go to bottom, it again will go slowly updating its weights. Okay, so let's try one more thing. I will show you for maybe for this. Okay, so let me run this code. So right now I changed the initialization point. Earlier it was -2 and -2. Now I have taken -5 and 4. Okay, and with respect to this, now if you can see that the plot also has been changing. That so here interesting thing is the loss function is red line. It was there around maybe 0.5 or something. After that it was not changing much. Same, the green is basically the bias. So after a certain point of time, maybe after 100 epochs, it's not changing much. And for blue line, which is weights, it's also not changing much. Okay, let's see, try to understand why it is happening. So with 3D plot we might able to get a better understanding with respect to that. The plot like will be same because our input line is same, so that's why input based, this plot will become based on the input that we are having, not the loss function. Okay, now let's try to visualize how what is the problem is happening. We can see that from this 2D plot that the both weight, bias and error or loss function value is not changing that much, or it's not moving at all. So what is the reason behind that? So I think it is still taking time, take little bit time, because we are running for 1000 epochs. Yeah, it came. Now if you can see, the error is 0.59, the epoch is 0, and if you can see my black cursor right now, that is the it is near the ascent, it is near the dark region. The red point is at the dark region, a dark red region, and also the black point is also at the dark red region. Now what is happening is, as we go step by step, that is after 50 epochs, we are seeing that it is kind of ascent, right? So it is trying to move towards the light red region based on that. So it is going. So after 50 epochs, the movement was pretty high because it is going from up to down. So it is going to local minima of red region. After that, after another 50 epochs, we have seen the movement is small. After 50, this is all happening in 50 epochs. That is, we are showing the animation within 50 epochs. We can see that after 50 epochs, now the movement has been stopped. So even if I click, the changes are not that much. So at 400 it is like 0.45. At 450 epochs also the error has been stabilized. That means it's not able to reduce much further, right? So this is the problem that we're observing, that even after 800 epochs, that the loss function value has been stabilized. Why? Because it's not able to go much further. It's like you throw a ball from the top side, and it bend down to plane surface and stop after certain time. So it is like this, right? So this is what something of gradient descent come into the picture, that you can see that in certain cases how the value of initialization affect us. So if you put initialization near the accent of red, that is where the value is the error is very high, or the value is maybe in this case around 6, b value is very 6, we can see that it is, instead of going to a blue region, it went to the light red region, because the machine thought that this is my minima, not the decimal, right? So this is one of the issue of the gradient descent. Okay, so let's get back to the I will stop presenting this part and let's go back to the theory that we were trying to see. So we have seen certain animations with respect to that, how the gradient descent is initialization is going to affect a lot with respect to how it's learning, right? So yeah, okay. So what initial representation that we have to see is, now the question that we can ask is, so is there any behavior that you observe on the contour plot? Okay, that's the first question we need to ask with ourselves. Is there any behavior you observe the contour plot? So what we analyze is that that as this is gentle slope, let's suppose this is a kind of 2D 3D plane kind of thing. Okay, here the part was red and here the part was blue, right? This is a typical 3D plot that we have seen in the code as of now, right? This is a red and this is blue, right? So what is happening, suppose my point is here, right? Now if there's no slope, this is a proper slope, okay, this like a proper slope is like it is getting down. But if I'm already, my initialization point is at the some plane, gentle slope, we call this gentle slope, at that point of time the weights, basically W and B, is not changing much or changing very slowly, either not changing much or changing very slowly, or either it's not changing much or it is very changing slowly, or the it is taking, or it is not moving at all, it is not even updating. Okay, so this is what happening when you put based on certain initialization. You found a situation that you are at the gentle slope and you can't move forward that much, right? And it, or even if you moving forward that much, you are taking a lot of time, lot of iteration, lot of epochs to reach to the minima where your error can be less, right? This is what we're trying to minimize. This is the limitation of the gradient descent, that wherever we found a surface where there's no slope or very less slope, their updation of W and B is not changing that much, right? So we want to do something about with respect to that. Okay, and we have also see that the first animation we have seen, when we have a different initialization, we are able to get reach to the blue, dark blue region, right? But in the second animation, where we start from dark red region, ideally you should go to dark blue region, but it is going to light red region because of the initialization. So yes, initialization affects your learning. Okay, so we have to choose our initialization very carefully with respect to that. And so the limitation of gradient descent algorithm is like that: whenever there's a gentle slope, the parameters are not learning that much. Okay, I think Parshuram has raised their hand. You can unmute yourself and you can ask the question. Okay, okay, so let's get back to this. So why this is happening? So why we are saying that when there's a gentle slope, why my W and B is not updating, it's not updating fastly, right? So this is a natural question that we should get a rise to, right? So what is happening here is, let's take an example which is taken directly from the lecture, that let's say, okay, let me put a 2D plot here. So 1, 2, 3, 4, 5. Okay, now there is some function f(x) is there, that is +1. Okay, now this is the function I'm going to plot this. So what I will find that my this will be, and this will be approx like this. Okay, so this is the kind of, for this function, this is my plot, where if my if y is x is 0, the y equal to 1, x is 1, y equal to 2, that is this part. Okay, and when x is 2, ideally I have made some little wrong, so y equal to 5, right? X is 2, y equal to 5, based on the equation that we have found here. Now we have, basically what we are doing, we are trying to arrive at a gradient. What is gradient in our case is basically derivative, Okay, now what is derivative? Derivative is, in general case, is derivative is change in y with respect to change in x. Okay, so let me take red color here. So what is happening, when my x is changing to 1, my this part is, y is also changing with 1. Okay, but my x is changing to 2, my y is changing by maybe 1, right? 2 minus 3, 5 minus 2, that is 3, right? So y is changing by 3. So what is happening, my gradient of this and this, in this case, or let's say here, that's millimeter, let me here, right? This, I have this gradient. Okay, so this will, I will call as, let's say, dy1 by dx2, dx1, and this one, this I will say dy2 by x2. Okay, so what is happening, that even though I have moved only 1 unit from 1 to 2, my rate of change for y2 is very high with respect to this. That's why I have a higher gradient or higher slope, right? So you can see that my change is high, that's why my y is changing very drastically or very rapidly. That's why I can move much faster with respect to So if I put a ball here and try to throw it here, I can see that there's a very high changes with respect to x, high change of y with respect to x. But what is happening in the first case, that is, even though I'm moving, x is moving by 1, y is also moving 1 by 1. So in our case, this part will be called as gentle slope, where gentle slope means my y is not changing much due to change in x, right? This is called a gentle slope. And the higher slope, or high slope kind of thing, we are saying that y is changing because of minimal movement of x. Okay, so y is changing, high changes are happening in y due to minimal changes in x. Okay, this is simple derivative knowledge with respect to. So you can now appreciate that even though my x, which considered as input, even though small things are moving, but my changes is high. That's what we call as higher slope, or higher slope with respect to that. And whenever my x is changing little bit, but y is also not, but y is changing very less, or it's not changing at all, that we call as gentle slope. Since our y is not changing that much, that's why the gradient of with respect to, when we see a plot where it's not moving that much in the second case, it's not going to update the value, because y itself, my output is not changing. Since my output is not changing, my error will also not change. My error will be same as it is if I'm getting the same kind of output, right? So this is a concept of gentle slope and come into picture. So the problem with the gradient descent algorithm is, if you find certain initialization where my W and B assigned in such a way that after certain epochs, I find a gentle slope, it will take me a lot of time to move out of that gentle slope. And if particularly if I'm in the right direction, if I went to a wrong direction, then there's a high, then I can't do it. It will stop at certain point of time, and then I have to change my initialization, right? So this initialization with respect to the loss function is very apparent with respect to this. Okay, so that's why we can't. So if when we say that can we initialize WB randomly, which we have done earlier, that ideally it was okay, that is we can do at certain cases, but not all the time. We have to do a lot of trial and errors to find a good initialization point of our WB from where our model can start learning with respect to that. Okay, so the answer is for randomly, yes and no within the context. Okay, once you do randomly, you check the nature of the output, and then you can directly apply some for your case also, it is going to be random only, but you still look at that certain initialized point where you're getting the better results. So you will choose that random initialization of weight and biases. Based on that, you start the learning algorithm of a particular your network. Okay, now that being said, so we are now we have seen that this is some problem with respect to gradient when it comes to the gentle slope. Okay, so that's why this motivate us to think of, can we have a better update rule where we can deal with the gentle slope. Okay, so can we deal with the gentle slope? This is our motivation to move towards the second better update rule with respect to that. Okay, so we are going to do for next 2 points, we are going to see the this part, can we come up with better update rules with respect to that, okay, which can deal with the gentle slope. So for that, we are coming with the momentum based gradient descent, which is the next part of it. And issue with, we have seen that problem with the gentle slope. So now we have understand that there is some problem with gradient descent. Let's see that what is the gradient descent will come into picture. So now intuitive solution here is, what we are saying is, so let's say this is a plane is there and it has to go here. Okay, this is a blue region, and here something called dark red region, and here your point is, right? Or no, let's say here your point is. Now to reach till this point, I have to do lot of epochs with the current update rule, right? So what the intuitive solution is, I think, which has been explained best by the sir in the course, that let's suppose I am at certain point. Let's say I am at the institute gate, okay, and I'm at the institute gate and I have to reach mall, which is somewhere here. right? So what I will do, I will ask person number 1, and they will say move toward this direction. Okay, then you obviously don't trust, so you will ask after a few meters, you will go and ask few more, one more person, that is the where is the mall direction. So again you will move little bit here. So again you will ask third person, you will go move here. But what you're having, since you're getting to know that from more and more people that mall is toward this direction, what you do is you will take the bigger steps now. Since I know that the mall is this direction, so I will take bigger steps, right? So same concept will come with respect to this momentum gradient descent as well, where what you're trying to do, that first you will move very minutely. Let me change the color. First you will move very minutely, then after getting confidence that okay, then you move little bit more, then you will move little bit more. You can see that little small points I'm doing, then little bit more, then you're getting confidence. So what you will do now, you will take bigger steps. Now you will take maybe more bigger step, kind of like. So you're building a momentum with respect to this, right? Once you know that you're going to a correct direction, you will build momentum with respect to that. Okay, my what I'm doing based on my past history, I know that I'm going to one direction, and the new value also giving me the I have to go to particular direction. So what I will do, instead of updating with small value, I will try to update. I will try to take a big step such that I will go near the slope, and from slope automatically my I will go down, come down to the blue region very fastly, right? So this is a concept of momentum based gradient descent here, right? You take out the history. So this all different colors you are seeing, basically these are the history, right? Your history of the earlier step that you have taken. Based on the history, you're trying to see that how much big step I should take, right? And you since you're going to a one particular direction, the more confidence you get, more bigger step you will take, and more bigger step you take, you will try to reach to the gradient descent much more faster. So this is the advantage of momentum based gradient descent. So mathematically it's shown like this, that now earlier let me change different color. So earlier our update rule was wt plus 1 wt minus and learning rate, that is eta, into delta wt. Okay, so this delta wt was there. Now what we are doing, before directly instead of coming here, what we are doing, we are introducing something called vt. So what vt is doing, vt is take care of the history of our earlier steps, history of earlier updates. So it will keep track of that. So how is keep tracking that? So you can see that this update rule, which is the main update, you will find it here. So you will directly keep it in this equation, okay? And you along with this, which is because this you are finding on the current step t, what you're trying to do, you're also considering that this is a gamma, this is called as gamma, okay? And vt minus 1, all the other steps that you have taken earlier, you're going to consider it with respect to that. Right, if you have seen the derivation in the course, will be like at v0 your value will be 0, okay? At v1 your value will be n delta, sorry, eta wt, okay, based on the weights that you are having. Then v2 what will happen is into delta w, say w1 हो जाएगा, right? Okay, so gamma into eta w1 plus eta delta w2, right? So like that you will do is, so this will become eta w square. This is a kind of derivation that you have seen here, nothing much to think much about. So you can see that how I'm going to calculate it. So I'm not have to keep store of this value, I can directly sum them up with the with respect to the value that we have given here, the gamma into vt minus 1. We just need to use the gamma aspect here, and plus sorry, delta w3. Now what is happening, suppose our gamma value is 0.9, here gamma value is 0.9, so gamma square value will be 0.81 and gamma cube value will be 0.027 kind of thing, okay? So what is happening here is, as you go away from the first decision, you will give the less weightage to the older decision, right? So like w1 now after v3 steps you are giving very less value weightage to delta w1. After that you are giving little higher weightage to delta w2, and then the recent one recent weight from which you are taking, you are giving higher weightage to that. So you are trying to distribute your decision based on the recent information rather than only relying on the past information, right? So it's like this in mall also. In mall example, you will rely much on this a third person value after you get more comfortable with this person value rather than this person, right? So you will give high weight to this and you will lower its weight or decision or whatever the information that this person has given, right? So this is what momentum based gradient descent update will try to do. Okay, so let's again come back to the demo part, and we will see what is how the momentum based gradient descent works and what is the limitation with respect to that. So let me stop sharing here. Okay. Okay. Okay, so we were till here. Okay, so haven't seen that vanilla GD with 2D points. Okay, you can run that later, or we will run that later. Let's go to momentum base first, because we are going to deal with 2D plot. This is a 2D version of this called as contour plot, and the same 3D plot that you have seen, we are showing it with respect to a 2D plot. Okay, 3D surface that you have seen earlier. So this is with respect to momentum base. Okay, so we are here, same points are here, that is with respect to the momentum base one. And okay, so let's try to run this first. I will show you difference, basically that will be much better. So what I'll do first, I will run the code with the gradient descent, and then we'll see how it's working, and based after that we're going to run the same thing for momentum based gradient descent. So only no parameters have been changed as of now. So gamma aspect will come into picture when is the momentum thing. I will go to the code, but first let's talk about how the performance is going to look like. Okay, so here you can see that like how we have seen earlier for gradient descent, the value of loss function and the W and B is not changing that much, right? So this is what we have seen. This is a 2D plot here. So here again 2D plot is like, if you can see my cursor, this is a dark red region, and at the bottom right it is like dark blue region, right? If you can follow my cursor, light blue means here this is, if you can see the much higher plane with less line, that means it is a gentle slope, or it is very plain in case. And if you can see much lines here, certain kinds of lines, that means closer line, that means it has a higher slope, right? So top left is have a higher slope, and the top bottom right is has a higher slope with respect to this. So let me run this. Okay, now let go step by step with respect to this and see how it is going to work out. Okay, so epoch 0, we have error is 0.4, we are at some middle region. So we can see that earlier what we have discussed, that in gradient descent, since there is a gentle slope, it will take lot of time for a gradient descent to reach from this point, black point, to at least till this white line, right? The white line, if you can follow my cursor, it will take lot of epochs because the changes are not happening that drastic. But what we want is, our objective is to reach to this point as soon as possible. So now this is for gradient descent. Let's see how much time it is taking. So each click is my 50 epochs. Okay, so earlier it is going little up, then this is 100, this is 150, 200 epochs, 300 epochs, 400 epochs, 500, 600, let's see, sorry, 400, my bad. Till 400 epochs, it is still near its original position. It's not that change its position. So even if I do it, so after even 1000 or 950 epochs, it is still here. That is, the changes are not happening that much, and you can see that we have to put at least 300, 4000 epochs or 10,000 epochs to allow this gradient to reach from this point where it ended to the white line, such that after white line it will go down, because there is a slope, so automatically gradient descent will take care of it. So what now we will do? We will change the, instead of GD, we will do the momentum algorithm. Okay, we will just uncomment that. We will run the same thing, same setting, only the algorithm will be momentum. And let's see how the earlier this thing will. Now we have seen earlier that our loss function was not changing much, neither the W and B. But here what you can observe that the green line is basically the bias and blue line is weights and red line is error. Okay, so we have started with -4 for error and 0 for bias, and how we can see that till 400 epochs it got stabilized, it got certain value after which the loss has been stabilized, right? So it has changed, so momentum has done certain thing. So let's see what actually it has done, what actually it is learning. So let's run this thing. It will take some time because there's 1000 epochs. Okay, perfect, it has come. So earlier epoch started at error 0, so each click is my each click I am clicking on it, it will be around 50 epochs. So first click it went till above, which is quite fast compared to the gradient descent, because we reached here till after 1000 epochs, so we reached till this point itself. So in 50 epochs the speed up is very high. Then this is 100 epoch, then 150, 200, 250. Now you can see the step is become bigger. Now at 200 error is 0.045, but you can see the step now from here 200 to 250, it's very big, right? Then again step in 50 epochs it has changed, it changed the whole dynamics, where it has taken the very big step from here till, and it reached from not only from it is not only crossing the white line, but it went region inside the region of dark blue region where the loss is very minimal, right? So again it went down, it overshot little bit, and it take a U-turn here, that is from low value it is going little up here, it again going up to minimize the loss here, and now it is getting stabilized. Now it has got stabilized, right? So this is the beauty of momentum algorithm, where with minimum number of steps with respect to gradient descent, you are able to reach to the local minima, that is the blue region here where the error will be less. But you have also seen that it is doing a lot of zigzag aspect with respect to this. It started here, then suddenly in 50 epochs from the red region it went to the blue region, and from blue region it went further down, and again it able to come back, right? So what to give an analogy of that, what happens that if suppose if you are on bike and you say that okay, mall is in a particular direction, you get confident, you accelerate your bike and you went somehow able to cross the mall, but you are not able to recognize, so you went again further. Then what you do, you recognize that okay, mall is at back, so again you go come back, you take a U-turn, again you try to see the where the mall is, again you take multiple U-turns, right? So this is what momentum gradient based descent is also doing as of now. Let's take different example. Now we have seen that the momentum gradient descent will try to reach to the loss function with zero value much faster compared to gradient descent, right? So let's see what if we take a different initialization point, that is -3 for weights and B for 4, what will happen? Okay, so we have seen that earlier this in this plot, from this plot, that around before 200 epochs itself is trying to stabilize all its value, right? It has able to reach the local minima or the dark blue region very fastly, right? So let's see how it is actually happening in the plot to get a better understanding. Okay, now our point is here. Now we have used the same thing earlier in the gradient descent, where we have seen that instead of going towards blue region, this point went towards the light red region, right, where my point cursor is right now. So it tried to went here and stop here. Let's see what momentum based gradient descent do. So every click is 50 epochs. So directly what it should, it overshot, it tried to went towards the blue region itself, but it went to the light blue region, right? After that, after another 50 epochs, it tried to from light blue, it went to the dark blue region. So it is taking very big steps within each epoch. Okay, then again try to overshot itself. It went outside the, maybe that's the more dark blue region, that's where it went. Again, now it has tried to stabilize here. So this is the point where it got stabilized, where the error is almost 0.055. So it got stabilized within maybe, let's say how many, So around by 300 epochs, the error was here and it was stabilized, right? The same thing if you try to do for gradient descent, it will move toward the right direction, so left direction, that is on the light red part. But here in each 50 epochs, it is taking a very big transition. So it is trying to learn the weights and the trying to go to the minima very fastly. So that's the advantage of momentum base. But the disadvantage is it follow a lot of zigzag pattern. That means it overshots its steps, how much big step it has to take. So this is something the some troublesome part for the momentum based. Okay, so it's almost 7. So let me summarize what we have done as of now, then we'll take 5 minutes break. So let me share the screen. Just a minute. Okay. Okay, so I'm doing this. Yeah. So what we have found, observation, that so observation 1 is there. So observation 1 is that even in regions where I am having a gentle slope, this gradient descent, what is able to do, it is able to take large steps, and why it is happening, why it is able to take large step, because of this Vt value. So let me write it here. So Vt was gamma into Vt minus 1 plus delta Wt, right? So because of the historical value, I am getting more and more confidence, and this value is also basically the addition of the previous history. So that's why, so even though my earlier steps might be very small, this one and this one, but in the third, fourth step, I will take this bigger line, this bigger step I will be able to do. This I'm making the big step as a very big horizontal line. So this is the first observation we are able to do, right? But there's a problem with respect to this also. So what is the main problem is it always good to move too fast? So we have seen that it overshot. So earlier maybe the region is like this is a red part, this is slope, and this is blue part. So this is blue, this is red, and this some slope where both red and blue exist. So what is happening, sometime it overshots and it will go here to blue region suddenly, then it will go outside the blue region, again it will come back maybe to a red region, again it will go back. So laws of to and fro is happening with respect to the momentum based gradient descent, right? So this situation usually arise where it causes us to run from if our goal is to reach here where I'm circling right now, what is happening, it's able to pass, even though my point able to reach near to that goal, I'm still overshooting because of my history. So what I have to do, I have to control my steps length. This is what I need to do. So this is the next challenge I found. The first problem was I have to take big steps. That's the first problem we have solved using momentum base. Now what is happening, if I'm taking large steps, I have to, because of large step, I am overshooting my goal. I'm not able to reach to that goal. So I have to reduce my step length accordingly, reduce it, right? So because for that I have to do control my step length, so that I should not overstep like this. I should once am I able to reach, I'm using blue now, if I'm reached this point, blue point, from here I should go slowly to my region, to this my main region where my loss will be minimal. So this is what I want to do, and for this I need to use now this concept of Nestrov gradient descent will come into picture. Okay, so the one thing, it oscillates a lot. Lot of oscillation is happening between the momentum base, this thing. But even though U-turn is happening, still I am very much faster than my normal gradient descent. So what I want to do now, I want to control my how big my step should be, right? So that is something I need to control. So this is what something we are going to see after this 5 minutes break. Okay. I will see the questions first. After that, we can take the 5 minutes break. Okay, thank you everyone. Happy Teachers Day for you also who are like, I think most of you are also faculties, and I think you are elder than me, so happy Teachers Day as well. So is there different, first question, is there a difference between back feed forward and back propagation? Yes, there's a major difference. Like okay, let me just show you, just give you small intuition with respect to this. So let's suppose this is a small neural network where this is my input layer, this is my hidden layer, and this is my output layer, right? So what feed forward is happening, I am moving towards the output layer, right? So I am whatever the weights I have, so there's something called as pre-activation, that is A1, that is called the pre-activation, and this is H1, this is activation function. I will calculate all this value, and then based on that I will try to go to my output layer. So this is, since I am moving upwards in direction, this is something called feed forward. So based on whatever the input I am having on x1 x2, and I have something called biases as well for both this thing, and for this also I have bias. Okay, so I'm trying to, based on whatever input I'm getting, I'm trying to learn from the data. I'm going to learn of these, each of the sigma neuron or any neuron. I'm trying to go up and try to do output layer. Now what backpropagation is telling me, that once I do there, I will try to find the loss value, that how far away from this, how far my output is from my actual value. So what I will try to do, I will again come back, I will tell to these neurons that hey, my output is getting wrong, please check your values and update your values. So I will go here, then they will say okay, it's not because of us, it's because of the weights that we have provided to us. So what will do, it will ask the weights here W and bias to change, it will go down till input layer and ask the weights and bias to change such that our output will be less. So for that they use so since we are going backward here, this concept of going backward from output to input layer is called something called backpropagation. Okay. Okay, Parshuram, I think you have raised the hand. You can unmute yourself and you can speak up also. Thank you, Pranat, for giving the previous classes link. Um, okay, so Parshuram, if you have any question, please type it out in the chat section, or you can unmute yourself as well. Input layer, no, input layer doesn't have any bias and weights. It is just, it's the input, raw input that we are giving. So this is something we have control over, inputs. Also weight, initial weight and bias also, but after from here input to the neuron, this is something we are initializing first, and after that learning algorithm will take place on its own, where it will try to update the weights and biases. Okay, so maybe we'll take maybe a 5 minutes break, because already an hour. So maybe we'll come back by 7:14, and we will start with Nestrov algorithm, gradient descent. We will talk about this, and then followed by we will try to catch up with the other algorithm as well. Okay, so if you have any question by the time, please put down in the chat section. Okay, the so by 7:15 everyone please be here. Okay, uh, welcome back. So maybe we'll start from where we left off. So what we have seen earlier, that we have seen the gradient issue, gradient descent. So gradient descent has certain problems. The problem will lies from the perspective of that normal or like vanilla gradient descent. It has a problem with the gentle slopes, and we try to overcome that with respect to the momentum based gradient descent now. But the problem with momentum based gradient descent, that there's a lot of oscillation is happening, oscillation, that it is lot of, you have to take lots of u-turn and lots of zigzag is happening with respect to that, right? So this is what happening. So what we want now, we are coming to Nestrov gradient descent, where we are trying to control the oscillation. So this is our objective, and we are doing it with respect to that in a two-step way. So what is happening here is, so let's say how to if you have to define here. So let's say earlier it was wt1 uh, wt minus vt was there in momentum base. If we expand it, it was happening that gamma into vt minus 1 minus n raised to delta wt. So ulta, yeah, that inverted this thing. So this is what we are having. It was there for a momentum base. So what was happening, that I am doing, while taking steps, I am taking two steps. This is called a step 1 and this is called a step 2, right? I'm taking two different steps with respect to this, right? That's why my momentum is taking very large steps as we go along, right? But what Nestrov is saying, that Nestrov gradient descent is saying that don't consider both the factor into picture. First you try to reach till this point, you take the first step, understand it where you are. From there, then you try to calculate the new gradient descent with respect to that position, right? So what it's saying, that I will first calculate this, my w temp value. Okay, I'm trying to first identify the value wherever from particular position where I'm going. I will go to that point, and from that point, once my step 1 is over, then I will try to calculate the gradient descent with respect to that step point where I'm pointing to. So first step, this is step 1, and with respect to step 1 I am taking the partial derivative with respect to this. So this is what I am doing. So once I am doing, I'm updating my actual this thing, and after that I am I'm updating my whole value. Okay, so again, in the context of mall, it is like this. Some person asks me that go to this direction. So first you'll go to a direction, but to the mall direction till certain point, and before asking the next person, you go to a certain point, let's say point A. And after asking this, you check that whether I should go to this direction or not. Then I will ask the person B, and it will say, okay, go to this direction for this person step. So what is happening after person A, I've taken a particular step A, then I'm again seeing that whether I'm going to, whether the B should be on the right hand side or in the left hand side. So this is what I'm trying to, Nestrov is trying to able to do that. So it is trying to adjust. So whatever steps I'm doing because of the momentum of the history, after taking the step, I'm trying to find a gradient descent such that I should know that where the steps I'm taking are very big enough or small enough, right? So this is the concept of Nestrov accelerated GD. Now let's try to see that how it is going to affect in the code. So how it is helping us to solve the problem of momentum gradient descent. So let me stop sharing this part. Let's go back to the code here. Okay, so let's go back to the code and we will see how the oscillation has been stopped or taken care by the Nestrov part. Okay, so we were here, this is, you can see the lot of oscillation is happening, right? Now what we are doing is, so let's take the same example, that will be much better. So here initialization was this, right? Let me copy this. Okay, so I will keep it aside. Okay, and I will give another one as momentum. Okay, so we have already seen momentum, right? So I don't have to do it again. So but we will say the same initialization point, and we will see that how it is going to work with respect to this code. So everything else will be same as it is, and now we will see what else we can do. So if once you're able to do this, now if you can see here, my loss is not changing that much because it's almost point come down to a point, and it is low. My weights and biases has been optimized very fastly within the 30-40 epochs, right? So I'm doing only 100 epochs with respect to this, and that I'm doing this. So let's plot the 2D part as well, and let's do the animation. Okay, okay, this is a different error, different points. Okay, I think I have taken the different data, I guess. Yeah, the data is different. Okay, so let me do it for above points here itself so that we can get a better understanding. So I will, instead of momentum, I will do here NAG, that is Nestrov accelerated gradient descent. So this is how our output will look like for the 1000 epochs. Let's see what energy will do. This is for momentum, and now we have seen that it's converging much faster than the momentum. Earlier it was there around 200 epochs, after 200 epochs, but it's able to stabilize the error much before with respect to that. And let's see what plot will look like, our animation. Okay, so one step is 50 epochs. So you can see that earlier what was happening for momentum, it was going towards this direction. The direction is same, but instead of overshooting, it went earlier. Momentum base went outside till the light blue region, and again trying to come back, right? And after that also, after 50 epochs, it went till this point itself. After that, in 100 epochs it went till here, and maybe after that it will shoot down below the blue region also. Let's see whether it will also do that or not. No. Now when in momentum, what happened that earlier when we overshot, momentum overshot and it went outside this graph on the dark blue region, and again it tried to come back. But here the energy, what is trying to do, energy is able to not take small step toward the direction, because it able to understand that I am reaching to a correct place, so I will take small steps. So again it takes little bit U-turns, but not as drastic as what we have seen for momentum, right? And now it has been stabilized almost for all the other epochs, right? So what we can observe here is that how moment, even though it will take the same direction as momentum, but it will reduce its intensity of the steps which it are taking. So instead of overshooting the steps, it will take certain long steps and certain short steps, and that is happening because that once it is moved based on the history, after that it is taking gradient descent to understand that where am I. So after taking step, then it is asking that where am I, instead of taking steps, bigger steps, and both things, instead of doing simultaneously, it is taking one by one at a time, right? So here also one more example to show how it is look like. So let me run this. This is a different input set of inputs, and let me run this. So it has some it has some oscillation, but not as big as oscillation, and it got stabilized after 40-50 epochs. Let's see the kind of data you have. So data is like, if you can see this contour plot, it will be like one valley. So it is like two, if you can see my hand, if it is like two plane surface that is at the height, and then there is a sharp valley where the blue region will be. So this red part is the two valley or two plane surfaces, and with a lot of gradient is there, and then this blue part is the sharp valley where the region is very small with kind of line for with respect to the blue, right? So what is in momentum, what will happen in general case, that if you have seen, if you throw a ball in a bowl, what will go, it will go from up to down, and then again it will try to go up and again try to go down, right? So there's a momentum of U shape, try to catch a U shape, right? But what NAG will try to do is try to stabilize this aspect. So let me do this first. First I will show for NAG, and then I will show for momentum also. So here on the right top we have a black point, from there we are starting, and after 50 epochs, so not here, the epochs are 5, so after every 5 epochs we are doing this. So it is going down slowly, it's going towards the, now as the gradient came, so it is moving little fast and it's going towards blue region, and it try to reach to a blue region and is trying to stabilize, right? So this is what happened. Now let's do the same thing with respect to momentum. We can see that the oscillation is here is very less, right? And but if we do with the same thing with the momentum as algorithm, let's see what will happen. Momentum, and I will do this. It will take some time. Yeah, is there. Now we are doing for momentum. Let's see what is happening after E5 epochs. So it's moving like NAG itself, slowly. Now the momentum has started building up. Now it's taking bigger step. Now it overshots. Directly it overstopped. From earlier, see, it was in red. Sorry, I should go back. So at the 40th epoch, I am still in the red region, but okay, sorry. At 40th epoch, I am in the still the red region, and at the 45th epoch, I overshot, took big steps, and went down to the this white light region. And again, I had oscillated, and again I overshot the blue region. Again, went back to near the white region, and again I tried to come back to stay near the blue region, dark blue region, and I'm trying to oscillate to reach the particular point. Now you can see that this is more hassle with respect to the energy that we have seen, that it is more reaching to the point much smoother than the momentum base. So this is an advantage which it is allowing us when we take consider history into the picture. First you consider history, then after consider the history, then you find the gradient descent of with respect to the point. So this is an advantage that NAG provides to us. Okay, so since this part is done, so let's try to summarize what we have done with respect to this, so that we can get an understanding that where we are into the current picture. Okay, so let me stop presenting. Okay. Okay, so the observation that we have made here as of now is, so what NAG is doing, it is correcting its course much faster than momentum, right? It is not overshooting, less oscillation, right? It is, so it is much better with respect to the what we have seen earlier, two gradient methods, right? Simple gradient method and with respect to this, right? And also that in momentum, what we have found that in the from the last example, so if the valley is small, that is if the blue region is very small, and within the blue region you have side by side red region, so kind of proper valley with respect to this, like this part, right? So this is a kind of plane, this is a plane, and so this part is blue region and this part is red region, right? So what we are seeing that if there's a you can consider like this is a ball, it is trying to go up, but because there's a high momentum, it will try to go up here and try to reach here as well, because the steps are very high, right? It try to overshot the region instead of going and staying here in the bottom itself, right? So what it tells us that if the valley is small, the chances of escaping the minima valley, this is we call as minima valley, okay, where the value is very less, we call as minima. So escaping the minima valley is becomes bigger, right? But however, uh, sorry, becomes bigger. But however, for NAG, what it will try to do, it will try to go down here. It will take a step, then look where am I, again take a step, based on the history of it will take a step, then update its gradients, again take a step, again updates its gradient, right? So it is not doing simultaneously like how momentum used to do, right? So this is what the observation with respect to this we have seen. Uh, so as of now, the story is we see that how do you use a gradient. So we are using a gradient to move from gentle slope to the slope to the going to the local minima, okay, or the minima of the graph, wherever the plot graph of the data, right? And we have come up with better rule. So first we try to increase the steps by taking the momentum, okay, based on the history, and once the history has been decided, then you're trying to control that history, control the step size with respect to the history, right? So what this is what NAG is trying to do, okay. Now what we are going to see, that now you know that there's some better ways to update the rules and all that, they will much more will come into picture, much more better will like something called as RMSProp, Adagrad and Adam. These are much better rules, we will come to that, but first you should know that where the problem lies in NAG and the momentum with respect to this, okay. Now the what we are going to see is how do you compute the gradients and what kind of data you should use for computing, okay. So is it how do you compute this thing, that's the first point, and how do you use the computing gradients. So there are three terms that you have maybe know already by now, something called as batch, mini batch, I'm writing batch gradient descent, mini batch gradient descent, and stochastic gradient descent, okay. So what is happening here is, let's suppose, again I'm taking the example from directly from the lecture here, NPTEL lecture there, that batch is basically the vanilla point, that is what I will do, I will consider the whole x and y. So this is the x, this is the input output data I have, okay. So I will consider the whole one input output data, okay. I will consider each and every point in this, and then after traversing the whole data, I will update my weights, Okay, so this is a typical normal gradient descent that we have seen, and this is called as batch gradient descent or vanilla gradient descent. Okay, so this is what we have seen as of now. Now, what before going mini batch, let's look at the stochastic. So what stochastic is saying that no, I don't want that. I want updates much faster with respect to my weights. So what I will do that I will see one point at a time. Okay, this is a one point. After one point, I will update my weights. Whatever points I have, I try to learn from that and I will update. Then again, I will do see the second points. Again, update my weights. Okay, third point, fourth point. So what is happening that stochastically it is doing this, that after every instances of a point, so when I'm saying instance of a point, let's say I have x as a input, and in x input I have multiple instances like x1, x2, x3, like that. Like suppose x is my image data set, so x1 is my one image. Okay, image 1, image 2, kind of like that. Okay, so after each and every image I'm trying to update my weights. So once I see a new image, I will change my weights. So looking after each and every image, I'm trying to approximate. I'm doing all approximation. Okay, so I'm approximate the w and b value, weights and bias value. Okay, so this concept is called as stochastic gradient descent. Now what third type is? So third type is saying that no, it is still very risky for me. This too much frequency might lead me to too much oscillation with respect to my learning. So what I should do, I will try to minimize. I will not take the full, I will not take the smallest step, I will take some in between. So what I will do, I will take batch of inputs. So maybe batch of like say 20 inputs, say 32 inputs or 64 inputs in the order of 2. I will consider this many points, and then I will try to update my weight. So this will be much better approximation for me rather than doing for every time. So it is like the example I given in the lecture is like tossing a coin. So I have, after tossing thousands of coin, I should know the what weight I should give to the heads, that heads will come, right? But what I'm saying, no, I don't have that much patience. I don't need to do that. I need to do much faster. So what I will do, I will, once I've tossed my coin, I will update my weights. That is stochastic. But I'm saying no, you should not do that. You try to see little bit more patterns. So what you will do, you will toss the coins 10 more times, and then after 10 more times, whatever the value will be there, based on that you will update your weights, that how many times the heads will come, right? So similarly, so your input data will be come down to batch. This will be called as batch 1, batch 2, batch 3, kind of like that. And this is very much important in the real world scenario, because in deep learning network, and whenever the data set will be very huge. You can't put all data set in your memory, right? So what I will do, we will take small chunk of that data and try to learn from that data and try to update your ways. So once this fund is there, so you may get w1 and b1, assume like that. Okay, so once you update your weights, then you go to batch 2. From batch 2 you will learn more weights, so you come to w2 and b2, like that, w1 bn. So this is the updates of weight for each, with respect to each batch you will try to get it. Okay, so this is called as mini batch gradient descent, and this is what we use in practical scenarios. So if you have heard the term of a hyperparameter called as batch size, so this is what it means about batch size, and it will be in the range of let me write it here. Okay, so it will be in the range of batch size, typically in the range of 32 instances, 64 or 128. Sometimes if the data each individual instances is very high, sometimes you can take 8 and 16 also. So when we say batch size is 32, 64 and 128, that means suppose you have 1 million points, something like don't know how many million points are there. In 1 million points, instead of taking all the points, traverse all the points once, and it will take a lot of time. So what I will do, I will take only 32 points from here, 32 data points, and try to learn from the 32 points and try to update my weight. Okay, so this is called as batch size, and batch size is basically a hyperparameter. The hyperparameters are the values which are external to the your learning model, which you can use to improve your learning much more faster and much more efficiently, right? So this is the batch size that we are talking about. So this gives an idea of that what data you should use for computing the gradients. This should answer us much better with respect to, and also we have earlier also in momentum and the Nestrov thing, we have seen the history of the gradients. History of gradient also we have considered. So that is also one aspect that we come into picture, that what data you should use for computing the gradients. Okay, now um, now let's go back to uh, the part of where we should look at. Okay, now before going to the Adam or okay, let me talk about epoch steps and then we talk about adaptive learning. So let me do that first as well. So what is epoch, what is epoch, what are steps? Okay, so let me write it down here, that will get you a better idea. So there's something called as epoch, then there's something called as steps, and then this is something called as n. This is particular terminologies that people use in the deep learning world or machine learning world. So one epoch is one pass over the entire data. Okay, one step will be one update of the parameter. Here parameters are W and B, that is weights and biases, and will be number of data points, and B will be mini batch size. Okay, so these three things are there, four things are there. Okay, so with respect, as of now we have seen three algorithms. So let me write here, we have algorithm 1 algorithm and number of steps in each in one epoch. Okay, so first is batch gradient descent. Batch means the vanilla gradient descent, the normal gradient descent that you have seen. So in that the number of steps will be 1, that is only one time after passing through all data points you're going to only one time you're going to update the weights, right? So that's why number of steps is how many times you update the weights. So that's the first one. Then stochastic gradient descent, where you will do n times. That means if our input has n data points, so n times you will update the parameters, n times. Okay, and the third is mini batch, where you're, instead of taking the whole input, you will take some parts of the small part of the input and try to learn from that input, right? So for that we have this uh, for that we have n by b. So you will divide the input by batch size, so you will have batch, and for n number of, let's say 1000 by 20 batches, so 1000 by 1000 divided by 20, it will be around 50. So 50 batches, for 50 times you will update your parameters by passing by passing your input based on the batches. Okay, so this is what we have seen with respect to the how you can update this update your grade values with respect to gradient descent, and how frequently you should update. Okay, but before doing that we will check this code also. We will try to learn for that as well. But all this is fine. Yes, you can you using gradient descent you can find uh, mm, you can go to the local minima, you can find the loss with pretty much less. Even though the number of epochs are very high, we can still achieve that part, right? And for that you have done little incremental improvements with respect to the momentum based or the accelerated part, right? But the now we are assuming here that the data points, each data point or each features that we are having has certain quality. Okay, so let's talk about that quality first. What do you know quality means? So let's say this is a sigmoid neuron, and here this is an input. Now each input, basically this is as a features. Okay, so this is feature number 1, feature number 2, feature number 3, feature number 4. Okay, so one input I have multiple features, and I'm going to pass that with sigmoid neuron. This is a sigmoid neuron. Sigma is written like this, so I'm writing like this, and I'm getting some output value. right? So this is what the usually the scene, how the scene will look like. Okay, now what happens, there's something, now you should introduce the concept of sparsity and dense. Now you should know this two terminologies that you're going to see here, and how the adaptive learning rate will come into picture. Okay, so what do you mean by sparsity and dense? So let's take an again example from the search lecture, which is saying that I have a database. Okay, so this is a movie database. Okay, and I have some multiple features are there, maybe 50 60 features are there, and movie database is for 1000 movies. Okay, now it has multiple features, like let's suppose one of the feature is that sir has taken is like, is the actor is Matt Damon or Shah Rukh Khan, or whatever you can assume like that. Okay, now if you list down all the 100 movies, so let's say movie are here and you list down all the movies here. Okay, and what you will do, you will give 0 or 1 if 0 if the Matt Damon is present in that movie, or 1 if the actor is not present in that movie, and you have 1000 movies as of now. Okay, so what, based on our understanding, we know that actor doesn't work in the 1000 movies, so maybe he, since he's a basically a main character, so he might be staying in he will be the hero of the movie, or he will be present in the movie mostly for 30 40 films. Okay, not more than that. That means for this feature is actor is Matt Damon, out of 1000 entries, only for 30 40 movies his value is particularly given to 1, right? That is, if 30 40, that means around 960 instances are there where my value is 0. Okay, so what do mean, so what we can make out of this, that means in a given column, since I'm trying to learn feature by feature, right, I'm trying to see which feature is important, and I'm trying to understand that as an output I want to know that give me the list of movies, or movies which are in which Matt Damon are here. So what I found that since 960 instances are there where my Matt Damon value is actually 0, that means my what model will learn, my model will try to learn that in majority of the films Matt Damon, or maybe for all of the films Matt Damon is not there. It try to give very less value or 0 value for this feature. It will try to assign very less weights for that. But I don't want that. What I want is that even though my 30 40 weights are there, I want to consider that as a prominent thing, and while learning the movies I should keep consider this 30 40 as a proper instances, not as a small instances, right? So this concept where a feature, because a feature can be presented as a vector eventually, right? If a vector has values and it has very small number of non-zeros, let's say in this case 1, then we will say it as a sparse vector. Okay, so maybe for 10% or maybe 5% of the values I have non-zero values, and rest of the 95% I have 0 value. So the number of values which I am really interested in is very less, right? So that's why it's considered sparse vector. And what I want to do, that whatever the less value, even though the feature has less value, I want to tell that okay, even though the value are less, I still find that feature is important, so I should learn about that feature, right? So this is something we need to learn. This is something which is the current gradient descent algorithm can't handle on. Okay, this sparse vector. Now what dense vector is, it is literally opposite of that. So if there's a vector and in most of the values the movie is 1 1 1. Okay, so let's say it whether it's a English, let's say it's a database of 1000 movies of English, right? So maybe apart from 1 or 2 movies, or let's say 1000 movies which has been nominated in Oscar, so out of 1000 movies maybe few movies will be there which are from outside English language. So my most of the whether the movie is English or not, most of the feature will be turned down to 1. So since my most of the values are non-zero, I will call it as dense vector. Okay, so this is the concept of sparse and dense vector. Now my task is, as a model I should learn that even though my task is, I have a model, and if you are given me features which has sparsity, okay, or dense, okay, I can learn it that's totally fine. But if it's sparse, I should learn from them also. I should not give weightage to the zeros more and 1 to less. Okay, so I should handle this type of conditions as well. Right, sparse vectors. So this is what our Adagrad and RMSProp deals with it. Okay, it takes care of the sparse vectors and try to learn from them, even though the values of from which it can learn is very small. So to give an analogy, again I will take the example where if suppose you can allow, suppose you're learning deep learning every single day, you can allot 30 minutes only. So what you will do, since out of 24 hours you are taking only 30 minutes to learn deep learning, or maybe let's say 10 minutes, right? So what you do, what whenever you're allotting the 10 minutes, you expect that you will give total concentration on to learn that part. Okay, but if you try to vectorize your whole day and see that how often you're learning deep learning, you will see that your vector will be very sparse because you're giving only allotting 10 minutes, right? So what you will do, those 10 minutes you will try to give as much foxes as possible. Okay, but let's take another scenario where you're trying to give 3 to 4 hours of learning for deep learning every single day. Okay, so even though you are not as concentrated as look that 10 minutes, it's okay for you, because since you're spending much time, eventually you will learn about them over the period of time, right? You will get the repetition of the same thing, earlier concept from the faculty, or the earlier and the earlier subsequent concept you will again retrace back to the older topics. So your concentration level should not be as strong as the 10 minutes that you're trying to see. So that's why dense is as a different concept and sparse is a different concept. You can take it as an analogy. Okay, so the question again here is, can we have a different learning rate for a parameter, be W and B parameter? Here in this case we are talking about features, so each feature has certain weights, right? So each parameter which take care of frequency of the feature. So how many times the features are occurring, based on that you should assign the weights. So that is something we have to deal with, that is the sparsity and density. Okay, if you're able to convince that what sparsity and density is, now what are, I will just first complete this thing and then we'll go to code. So what Adagrad, RMS and Adam is trying to do here is, it is trying to consider that part. So how it is going to consider that part? It is taking care of history as it is taking directly from the NAG or the gradient descent part. It is considering the history. Okay, and what it is doing here is, apart from the history, it is also seeing the changes in gradient, that is delta W square. Okay, it is also considering the changes in the gradient. Then what it is doing, that it is putting that in denominator. So when you're trying to update the weights using eta, that is learning rate, and under root of Vt plus epsilon. Okay, we'll talk about epsilon later, let's talk about Vt. So how do you deal with the Vt is, suppose Vt is very less, you have a sparse vector. Okay, so the number of time the Vt value will be very small. So Vt for sparse vectors will be small, because most of the history, let's suppose that sparse vector has only 1 and 0 value, so most time it's 0 value. So I will what happened, the history value, because you're adding it one by one, right, it will be very small. So if you put anything which is denominator, if denominator is small and let's say numerator is whatever as it is, what the output will be, your output will be high. Okay, but if your denominator is large, your output will be less, numerically, right? That means, like if I divide 1 by 0.5, which will be equivalent to 2. Okay, but if I divide by 1 by 50, which is higher number than 0.5, it will be like 0 point something, 0.2, something like that, right? So this is what I'm trying to talk about. So how Adagrad is taking care is this, that when there is a sparse vector, my Vt history will be small, so I will take care of that and I will increase the learning rate. So what is saying, that if I have a sparse vector for a feature, okay, my denominator is small, so what I will do, I will put that into the above equation, I will put that in this equation, which will act as a learning rate, and I will increase my learning rate, because I have very few instances. So I had to need to learn as fast as possible because I can't spend time much on that, and I have very few instances, so my learning rate should be increased based on that. Okay, so this was sparse vector. Now what about dense vector? So with dense vectors, what's happening is, since I have a lot of history with me, my denominator will become very big. Now if my denominator became very big, so what the problem lies, that my output will, the learning rate will become very small, sometimes close to zero. Okay, so learning rate will become small. So because learning rate is small, so I can confidently say that, okay, I have more instances coming to picture, so I don't need to increase my learning rate or increase my learning as fast as possible. I should not do aggressive learning rate. Okay, so I'm trying to avoid aggressive learning rate that we have seen in momentum, right? What we are seeing in momentum, suddenly it has a lot of oscillation because it is aggressively changing its steps, right? So learning rate helps in that, to reduce that step. So if my dense vector is there, I will say that, okay, my values are pretty much, I have more instances to come, so I need to worry. I will take small steps to learn the data. But for sparse vectors, I will say that I have very less data points, so I should learn from the data points as much as possible. That's why I will increase my learning rate. Okay, so this is the same concept which we are going to use for RMS and ADAM as well. So let me just quickly go through that as well. So it deals with the sparse and dense vector. Okay, so that is what, because this is something we will see more often in the deep learning algorithm, because when the features will come into it will usually divide into sparse and dense. Okay, that's the one thing. Now after Adagrad, what sometimes happens is, the disadvantage of Adagrad, what is happening, that if I have a dense vector. Okay, so epsilon is just a very small value, small numerical value. So just in case in sparse vector my value is 0, I should have something with epsilon such that this value will not be become indivisible. So you know that anything by 0 is undefined. We don't have any definition with respect to that. So that's why, to avoid this n by 0 divide by 0 error, we are putting epsilon in this case, nothing more than that. Okay, now let's come back to the main topic. So what problem with Adagrad is, if I have a dense vector, my WT might still become very high. Okay, so what happens is, if I'm trying to learn, let's suppose, okay, um, so let's suppose this is a kind of area we have, that this area is blue. Okay, this is a dark blue area, and this is the dark red area, and this is a light blue right region, and some white region, right? Now my point is here, I need to reach here, this point. Let me take different color. Let's say I need to reach the yellow point. Okay, so what happens, since I have a dense vector, I will start slowly moving toward this direction. But because of that, since my WT will become so big that it will be uh, my learning rate with respect to the under root of WT will be become close to 0.00005, something like that. Let's assume like this, which is equivalent to 0, right? So the movement will be very small, so it will not able to reach till this point. Okay, so it has seen a lot of cases that able to reach to the local minima, but to the reach to the perfect loss, because we are able to reach to zero loss, right? So what happens, that Adagrad stops in between, because this WT value will become so big that I can't take more steps, because I will stop here. I will stop at certain point of time. So what should I do here to resolve this case? This RMSProp come into picture, where they add another feature called beta, that is beta into W minus T and 1 minus beta. So what is trying to tell that, it is controlling, it is trying to control this delta under root WT. It's trying to control this part. Based on controlling the denominator, I can move according to my needs. Okay, so this is something predefined. You have to do as this is called as one of the hyperparameters, beta, that you will see when you start actually coding. Maybe for next session we will start PyTorch for sure. So I will show you the beta aspect there as well. Okay, so what it will do, it will try to control a denominator such that you will not reach to close to 0. So it try to avoid that aspect into the part. Okay, now this being RMSProp and Adagrad, so you can see that the adaptive learning. So based on how my data of a particular feature is, how many data points I have, based on that I'm controlling the learning rate. So all this image that you have seen, I will use blue right now, or sorry, first, all this heavy maths equation that you are seeing here right now is just to tell about that, to control this aspect, which is basically the learning rate, how big my learning rate should be, how small my learning rate should be. So this is this controlling this learning rate is come under adaptive learning. Okay, if you're able to understand this part, that is more than enough. If you can take anything from this class, that what we're trying to control here is, we're trying to control the learning rate, we're trying to control that how we can move within a slopes. Okay, so that is the first half that we have seen with this gradient descent. Now what Adam is doing, Adam is taking the best parts of RMSProp, sorry, RMSProp is here, and momentum. Okay, it is trying to take the best world of both RMSProp and momentum, where momentum will give me higher steps, more larger steps towards reaching the goal, but at the same time I will also consider the possibility of the sparse and dense vector. So based on that I will try to reach to this point of updating the weights. That's what Adam is doing. And in practical scenario, what I'm aiming for, what usually people use is, it's not mandatory but most of the people uses, they use Adam optimizer. So Adam optimizer is, now Adam is an optimizer. What means, how you optimize your updating the weighting of updating the your parameters, that is W and B. So use Adam optimizer with the help of mini batch gradient descent. Okay, because this delta wt that you are finding is with respect to the mini batch gradient descent. So you use this for any other architecture, like be it CNN or the simple feed forward network. Use Adam and mini batch for computing your problems. Okay, so this is a more popular thing that you can do, and we will see that how it is very effective in certain case scenario in the upcoming sessions. I know it's already 8, so what I will do, I quickly go through the code, and I will try to show you that how RMSProp, Adam and Adagrad works into the picture. So give me another 5-10 minutes, I will try to wrap it as soon as possible. Now so just to summarize what we have done, we have seen that the problem with the gradient descents and the problem of how we can solve it with the help of momentum or updating the weights with respect to considering its past history. Now we have seen the new problem that yes, you can update the weights, you can consider the history, all that is fine, but now we have to see that there is a different type of features will come into picture, something called sparse and all. That is something we will consider. So just give me a minute. Sorry, I'm just attaching my, yeah, it's working. Okay, I will not do the mini batch one, but I will show you the output. No, the mini batch one is something, okay, let's skip that as of now. Let's go to Adagrad directly. Okay, so we in Adagrad we are looking at the history as well, and this is the kind of input that we are having. So first let's run the nag first, that is an accelerated Nestrov accelerated gradient descent, and see what the output look like, and then we will go look at the Adagrad, and following same thing we'll run for RMSProp as well. So let's run this. Okay, now in this plot, this is the error with respect to epochs plot. We have 5-6 lines here. So let's discuss what is that. So red line is loss as usual. The dark solid green line is basically the green line is B, that is bias, and solid blue line is weights. Right now you have seen that there is something called as a dotted green line and dotted blue line. So what is this? That this dotted green and dotted blue are with respect to history. So whatever the solid blue line you are seeing, and dotted blue line, solid and dotted blue line, it is with respect to history. So we are saying that how much it is changing with respect to each other. That means at, let's say, from 0 to 25 epoch, how much weights I'm changing with respect to each epoch. So that is something we are trying to show it. Okay, so it's looking at the history, and it is looking at the history one epoch at a time and trying to see that how much variation the weights I am able to look at. So as far as now, B and W are looking the same in a similar way, updating a similar way. Their movement they change when there's a convergence point is there, where B and W went across each other and went to different paths. Okay. uh, okay, so let's look at the epoch here. So let's look at the NAC. So the this dark red line, if you can see my cursor, this is the highest point. Dark blue is the valley is here, but you can see that the top right part is the ascent, and the top left bottom left part is the descent. Okay, so let's see how it is go. So this is we are doing for NAG. So we are doing for 10 epoch each. So as you can see, this is going and it is reaching here, and this is perfectly fine. So what is happening, first it is changing the B. Okay, it's not changing the W much, but it's changing the B to a certain extent. After that, once it reached to a particular point of B, it again started moving toward W, where it's changing the W in a particular direction, and slowly it is changing the value of B as well. Okay, so let's see what Adagrad do with respect to this, and how it is changing the equation if we use Adagrad. So oh, okay, I'm sorry, I think I have shown the output of Adagrad rather than the NAC. So let me run it first one more time so that we can get better understanding. This code already has been shared with you in the chat, so please look at that, please play with it, change few things. If you're not able to do, please let me know in the next session. I know I have skipped a lot of stuff in this session, but this is for you to this code is going to you for as a playground to see that how initialization and how different algorithms play with each other. Okay, so spend some time on this code to understand it. So this is a NAG, actually this is a NAG output. Now what is actually happening, that how it is moving. So okay, now it is taking 1.99. So what is happening, that it first tried to get down to a local minima. In this case it was little higher in this point, now it tried to go at lower minima and changing only B most of the time. W has not been changed much. Then it get a gentle slope here for most of the part, so it's trying to move to a direction, and once it get the momentum, it take big steps and try to go to the blue direction. And before that we have seen for Adagrad, where it went to the blue changing, but it was more smooth and much more and smaller steps. It went out and then it trying to get toward this point. Okay, so that is one point of Adagrad. And for RMSProp, what is happening, that for the same data point, I'm going to show that for same data point, let's see how it is running. Again we are here, and for RMSProp, it is within 10 steps it is going out, same like Adagrad, it is going out, and then after 20 epochs it is moving slowly towards the direction. Then 30 epochs, 40, 50, here 60 it reached down to blue region, and 70 it almost near, and till 80 it reached to a proper region here. But earlier we have seen for NAG that it took approx 190 epochs to reach to a proper region. So it is much faster and much smoother with respect to NAG here. Okay, and then we can see not much that difference, very small differences are there within the this region. So RMSProp is much more faster than Adagrad and obviously NAG, and it's reaching to the local minimum much faster with respect to is keeping the W and B to a standard rating. Now let's see for Adam, which is the most advanced algorithm as we have seen as of now, which is for learning rate, and let's see how it is running. Same scenario, let's run it. Again within 10 epoch it went outside, same as what we have seen for Adagrad and RMSProp, because it's taken its inspiration from there. Then sorry, yeah, 20 epoch it went little up, it tried to adjust its weights because it has the both component of momentum and RMSProp. then this oscillation that we are seeing is more because of momentum base, and the updation towards the region, it's more because of the RMSProp. So an RMSProp we have reached earlier this because for the points, but as we have but in reality in most of the computation, RMSProp reach to this point much faster than say Adam will reach much faster to this blue region compared to RMSProp. For this example it might have taken little slow, but as you see, you can see it considers both the momentum as well as the direction to which the atom has to take care of. So it is taking care of both density and sparsity vectors, as well as it also take care of the momentum, because momentum gives much better steps, larger steps toward that. But though it has a problem of um, a lot of oscillation. So now the next step would be after this is that how to reduce this oscillation using the regularization, and how activation function come into the picture. Till now we have seen the learning algorithms with respect to the stochastic gradient descents, C type of gradient descents, and the Adagrad and the and the RMSProp, and we have seen that how the batch size will come into the picture. Now the next set of lectures where we will start with the actual PyTorch coding. We don't have to write so big of codes. You don't have to remember this code also. You can just use it, play with it, change some values. If you have to change the values, you have to change the values in this part only, this algo part here. You change the x and y values, and you change the algorithm here with change the initialization values, and you can change the eta and epsilon value, gamma value, epochs to deal an animation frame to deal with how to play with how different scenarios will play out for a different kind of algorithms. Okay, uh, so that is from my side. Um, so what we have seen earlier as of now is we have seen different kind of gradient descent algorithms, and we have seen different type of gradient descent algorithms, and we have seen how the problem of gentle slope has been taken care by the momentum and Nestrov gradient descent. After that, we have to deal with the adaptive learning, where based on the number of values, a number of parameters a feature has, based on that I have to update my learning rate. For that, Adagrad algorithm come into picture. So yeah, so that's the session. That's the session from my side, and which you please use the code which I have given to you. I think someone is asking for code again. So please take some time to understand the code once, because I haven't explained the code as it is. I just show you how to run it. So maybe take some time if you're not able to understand. Maybe next session after the class we will understand the code one by one, line one by one. Okay, and from next class for sure we will start the PyTorch along with the understanding of activation functions, improve activation functions and all. Till now we have mostly used sigmoid. Now we will see other like tanh function and other functions we will use for we will going to use. Okay, so if you have any question, please let me know. Otherwise the session is end from my side. Okay, so let me stop the recording. Thank you everyone for coming.